Hi everybody, in this video we're going to demonstrate how to use pre-trained object detection models hosted on TensorFlow Hub. Hi there and welcome to Learn OpenCV. TensorFlow Hub is a central repository for sharing and reusing a variety of pre-trained machine learning models provided by Google. TensorFlow Hub contains many different types of models, but the focus of this video is going to be on how to use pre-trained object detection models to perform inference on some sample images. If you're not already familiar with object detection, it involves the identification and localization of objects within an image frame. As shown in the feature image, the detections are typically identified with a color-coded bounding box indicating the location within the image where the object was detected. A label is also included to indicate the class of the detection and also the confidence score. Before we get started with the coding implementation, let's just take a quick look at the TensorFlow Hub site. Here we've provided a link to the object detection page on that site, but notice that in the upper left-hand corner you can also set filters to navigate and search for other types of models. We currently have a filter set for object detection models, but as you can see, there's numerous models here to select from, and you can further just use the search bar at the top of the page to search for a certain family of models. So here we've decided to use the efficient det family of models, so I'm going to go ahead and search on that, and then navigate to the specific model that we're going to use, which is efficient det D4. And so we'll go ahead and visit that specific model page. And then as you can see on the right-hand side, you can copy the URL to this model page. You can download the model, and you can even open up a Colab notebook that has an example implementation of the model. And then as we scroll down here a little bit further, we see one example output from the model. And then a little bit further below, there's some notes here on using the model. And notice that this specific model does not support batching, but it does require that the input tensor contain a batch dimension. Also notice that the values for the input image are in the range 0 to 255, but that isn't always the case. So when using a model from TensorFlow Hub, you should always check the documentation to better understand what the pre-processing requirements are for the images. And then here in the output section, it's indicating that the model's output is in the form of a dictionary, which contains several different items related to detections. And so we'll get into these details in the coding implementation, but if you're not familiar with detection models, this is fairly typical for the type of output that's produced by such models. So let's go ahead and continue on with the coding implementation back in the notebook. So we're going to start by downloading a small archive which contains a few sample images that we'll be able to use with this object detection model. And after that file is downloaded and extracted, it'll create a folder on your local system called Object Detection Images. And here we're using the glob utility to create a list of path names to each of those images. And then next we define a convenience function which loads each of the images into memory. And also notice that the last line of that function adds a batch dimension, which recall from the documentation is a requirement for the model. So next we're using that function to load the images and display them to the console. And you can see that we have 4 very different images. And we chose these primarily because they contain various object types that are contained in the COCO dataset that we wish to try and detect. So next we're going to define a dictionary that maps class IDs to class names for the COCO dataset. And you can see here that there are 90 different object types, each with an ID and a name, and we'll be using this in the implementation below. We also are going to need to color code the detections, which is always helpful. And so this code cell here automates the creation of various random colors that will be used to render the bounding boxes for each object class. So since the data set contains 90 different object types, this is something that is better automated rather than trying to hard code 90 different colors. And one thing that it's worth mentioning here is that the color values are all on the lighter side so that we can display dark text on any one of these colors and it'll still be clearly legible. So next we're ready to continue on to the next section where we're going to specify the model in TensorFlow Hub that we'd like to use. Here we're going to make use of a family of models called efficient det, which, as the name indicates, were designed with efficiency in mind. And notice that there's 8 different models within the family, D0 through D7, where each model in the family takes a progressively larger input size. So D0, for example, which has the smallest input size, is also the smallest model. And as we move towards D7, the input image size is larger, and also the complexity of the model is larger. And so the inference times for D0 should be very quick, and as we progress through the series, the inference times for the more complex models will be longer. So depending on your particular application and your inference time requirements, you may decide to use a simpler model if you need fast inference times, but if you're looking for maybe something slightly more accurate, and can tolerate longer inference times, then you might choose a more complex model. So in this example, we're going to use the D4 model just to give you an idea of how well the kind of a medium model performs. So using this dictionary that we've defined here for convenience, we can specify the model URL by indicating the appropriate key for the model. And then to load the model into memory, we use the load method from the TensorFlow Hub framework. And we'll store that in OD_model. And that'll take a while to load, but once it's loaded, we can use it to perform inference, as we'll see below. So this next section now walks through an example for performing inference on a single image. And there is no predict method for this model. You just pass the image to the model. And recall that when we loaded the images, we loaded them in a list. And so here we're specifying the first image in a list of images. And the model returns for us results in the form of a dictionary. And if you're not already familiar with the output from this model, then we can print the keys from the dictionary. And so in this first line of code, we're first converting the values in the dictionary to NumPy arrays. And then in the next code cell, we're looping over all of the keys in that results dictionary and printing out the keys. And so now you can see that there are several items related to detections. For example, detection anchor indices, detection boxes, detection classes, and so forth. Then there's one item, a number of detections, and then we have a couple of items that start with raw detection. So when the model is performing its computations, it produces a set of raw detections, which is often a very large number of detections. And then within the model, there's some additional processing that takes place, which tries to eliminate very low confidence detections or redundant detections. And then after that processing, the model returns a set of detections indicated as num detections. So we can take a look at this in a little bit more detail. So down in the next code cell, we're going to print out the number of raw detection scores and the number of detections. And notice that the number of raw detections is often many thousands, while the number of detections for this particular image is only 16. And then further, we can take a look at some of those details. So in the following code cell, we're going to print out the detection scores, the detection classes, and the detection bounding boxes. So here you can see that the scores are probabilities, and these are sorted in the order of highest probability to lowest probability. The detection classes indicate what classes those detections are for, and the detection boxes indicate the bounding box coordinates for each of those detections. And so now that we have a good idea of what's contained in the results returned by the model, the next step is to use those results to annotate the original image. And so that's the purpose of this next section. And here we're defining a convenience function which will annotate the image with the results returned by the model. So this function called process detection has two required arguments, which are the input image to the model and the results returned by the model, and then an optional argument, which is a minimum detection threshold. So to get started, we're going to first extract the detections from the results dictionary, and that's what these lines are doing here. We're going to set the minimum detection threshold based on the default value of the optional argument or one that's been provided. And then this next step applies the detection threshold to all the scores and returns the indices for those detections whose scores were greater than the threshold. And then we can apply those indices to all three lists of detections. And then in the next section here, we're using those indices to extract the scores, the bounding boxes, and the classes for all the detections associated with scores that exceed the minimum detection threshold. And this is important because oftentimes the detections returned by the model still have some low probability detections or redundant detections that typically need filtering out. So some sort of a detection threshold is usually applied to the results from an object detection model. Next, we're going to make a copy of the original image so that we can annotate that. And then next, we're extracting the height and width of the image, and then also setting a couple of parameters that are going to be used to render information on the image. So all the logic that we're going to use to annotate each image is contained in this loop. And we start by extracting the bounding box, class ID, and score for each threshold of detection. So this first line of code extracts 4 floating point values, which are the coordinates of the bounding box for the current detection. Next, we use the class ID to extract the class name from the class index dictionary. And then here we're going to convert the bounding box coordinates from normalized coordinates to pixel coordinates. And the reason for this is that the model produces bounding box coordinates that are normalized to the size of the image. In other words, between 0 and 1. So those need to be scaled in order to produce coordinates in pixel space. And then next we're going to use a class ID to create a color from the color IDs array that we created earlier. So now we have everything we need to render a colored bounding box on the image. And for this, we use the OpenCV rectangle function, which requires an image as the first argument, 2 sets of coordinates that define the upper left and the bottom right corners of the bounding box rectangle, and also a thickness for the line that's used to draw the rectangle. So now that we've annotated the image with a bounding box rectangle, we'd still like to identify what type of detection that is. In other words, what class is that detection associated with, and what's the corresponding confidence score for that detection. And so we're going to continue on here, and the first thing that we're going to do is use the class name and the score to build a text string with that information. And the way that we're going to label this on the image is to create the text as we just did, and then also create a small colored rectangle that's the same color as the bounding box, and display that colored rectangle at the top left-hand corner of the box with the text overlaid on top of it so that it's legible. So in order to do that, we need to first determine how large the text is so that we can create an appropriately sized rectangle. And so we can do that with the OpenCV function getTextSize, and that will return for us the width and height of the text in pixels. And then further below here, we can create a rectangle that's a little bit larger than that and position that rectangle in the upper left-hand corner of the bounding box. In other words, it'll sit right on top of the bounding box. You'll notice that there's a little bit of code here that handles the case when the bounding box is at the very top of the image frame, and in such a case, the label would be off the image frame. So for those situations, we make an adjustment here to put the label inside the bounding box so that it's still legible within the image frame. And then further below here, we're going to create the filled rectangle, which is going to act as the background for the text that we're going to add to the image. And notice that when we call the rectangle function, this time we give it a thickness of -1, which corresponds to filling the rectangle. And then finally, we're going to position the text over that filled rectangle, and that's what the last function does. This is another OpenCV function called putText. And here we supply the text string that we created up above, the coordinates for the lower left-hand corner of that text string, and then several other parameters to indicate the font style, the scale of the font, the color of the font, and also the font thickness. So when we're all done with this, we now have an annotated image which contains a colored bounding box and the corresponding label in the upper left-hand corner of that bounding box. So we're going to experiment with this a little bit below using different thresholds on one of the images, and then we'll use this function again to process all 4 images and take a look at the results. In this first example, we're going to use the function that we just created above to annotate one of the images, specifically using a detection threshold of 0, which means that we're going to not filter any of the detections returned by the model. And just to be clear about the steps involved, we're going to start with the execution of the model. And here we're passing it the first image in the list of images, and that returns for us a results dictionary. We then convert those dictionary values to NumPy arrays. And then at this point, we're now ready to pass that image to the function we created, and that should return for us an annotated image with all the results. And as we scroll down here further, you can see that there are numerous detections here, and several that are clearly mislabeled. For example, in the upper left-hand corner, you see it's confusing the leaves on the tree with a potted plant. So there's several, at least 4 or 5 detections here that are associated with potted plants. Notice also that in the very upper left-hand corner it says person. It turns out that the entire image frame was detected as a person. And notice the score is 0.00, so it's been rounded to 0. So one of the detections returned by the model had a very low probability detection that this entire image was associated with a person, which is obviously incorrect. And there's several other examples if you take a close look. Notice that it's mistaking the garbage can across the street for a cell phone. Also, it thinks that the bike perhaps might be a motorcycle. But notice that all of the probabilities associated with these detections are very low. And so this just emphasizes the need to filter the detections from the model using a detection threshold. And so that's what we're going to do in the next example. We're going to just call the function again, and this time we're going to pass it a detection threshold of 0.3. And now we have much better results. We see that there's only one detection for the bicycle, one detection for the dog, and notice that those bounding boxes are quite accurate. And then there's a detection for the car across the street. You'll notice that actually there's 2 detections for the car across the street. You can just barely make that out. Those are accurate, but they're redundant. And so that's something that can happen with object detection models. But clearly, using a detection threshold is something that is often required. And depending on the type of application you have, it's going to require some experimentation as to what an appropriate threshold might be. So with that as an introduction, let's continue on and formalize the implementation a little bit with the creation of another convenience function called run inference. So this function is going to take a list of images and a reference to the model, and it's going to loop over the images and call the model for each image. That then returns for us a results dictionary. We convert the values within the dictionary to NumPy arrays, and then we're going to append those results to a results list. And when we're all done with this, the function is going to return a list of dictionaries. So in the next code cell, we can then execute this function, passing in the list of images and a reference to the model, and that now returns all the results for all the images. So now that we have the results for each image, we can post-process those results. And so here we're looping over the images one more time. Remember that the images were formatted in such a way to include a batch dimension, which is required by the model. But when we post-process the results and annotate the images, we need to remove the batch dimension first. So that's what this first line of code does in the loop. And then we call process detection, and we pass in the corresponding results for that image. And here you can see that we're also setting a detection threshold. So let's go ahead and just scroll through these results and talk about them a little bit. So this first one here we've already processed. So let's continue on to our next image, which shows a grouping of elephants. Notice that each of the elephants is clearly identified with bounding boxes and labels, and that the detection confidence for each of these is well above 80%. In this next image coming up, we have a home interior with all kinds of objects in it. Notice that there are books along the left-hand side of the image. In the background, there's a potted plant which is identified. Most of the furniture is identified. The two couches on the left, a couch on the right, and even this a chair, which is a rather unusual shape and also perspective, looking from the back of the chair. That's I've been identified. The vase on the table. And there's another object there on the table. It doesn't appear to be a vase, but it's identified as a vase with 46% probability. And then looking to the right, you can see that all the books on that end table have also been clearly identified and labeled. So let's take a look at the last image. Here we have several oranges in a bowl, most of which have been identified. The model does have a spoon, a fork, and a knife in the data set, although only the spoon was detected. And kind of suspect that it has something to do with those white handles, which is unusual for flatware. Notice that also that it detects the blue bowl. It's not very obvious because we've got a gray bounding box around it. And then also it's detecting the large bowl that contains the oranges. But again, because that's a light gray rectangle, it's hardly visible. And then if you pay really close attention, you'll notice that the entire image was identified as a dining table, which is really interesting. Obviously, there's no structure to the table, but from the context of what's on the table, it identified the fact that there's a dining table underneath all these objects. So, we hope that gives you a good appreciation for how to use a pre-trained object detection model in TensorFlow Hub. Again, some of the key points to keep in mind is taking a look at the model's documentation to understand what the pre-processing requirements are for the model. Also keep in mind that with object detection models, it's very important to set a minimum detection threshold. And setting that value often takes some experimentation depending on your particular application. And finally, since there's so many different object detection models available with various architecture complexities and input size requirements, you'll want to give that careful consideration depending on the accuracy requirements for your application and sometimes more importantly, the inference speed with which you need to make detections. So smaller models will perform inference faster than larger ones, but tend not to perform quite as well. So it's a balancing act, and it's something that you should be aware of depending on what you're going to use the model for. So we hope you enjoy experimenting with this notebook, and if you found this video helpful, please like and share the video and subscribe to our channel to get more content in computer vision, deep learning, and AI.